Okay, so P7.8, nuclear fusion. Okay, so where fission was splitting things, fusion is joining them. So it's when you join things together. Okay, so fission, splitting, fusion, joining. Okay, so the next thing that you need to know is what's happening here. So, well, let's start off with just protons to start with, okay? So if you've got a proton and you've got another proton, if you try and push them together, they will repel each other. That's what we've been told so far, okay? And that's true. And that's due to a force known as the electrostatic force, okay? And that extends out past the protons, and when those two things get close enough, then so that force takes over and that force makes them repel. However, it's not always true, because if you push them together really quickly, then you do it really fast, then they can get a bit closer. And if they get closer, then there's another force that acts around protons, which is called the strong nuclear force. Now, the thing with the strong nuclear force is it is really strong, but it doesn't happen over a very big distance. So it only happens over a very short distance. So you have to push them together so fast, so quickly, that they get close enough for this strong force to take over from this repulsive force. Okay, so this one here, this acts in a bigger area, but it's not as strong as this one. So this one is the strong force, and this one is the electrostatic force. Okay, and this one big area, weaker. This one small area, stronger. So if you get them close enough, this one will push the other. And the analogy I like to use is if you imagine wrapping a bar magnet up in Velcro, it would still repel another piece of magnet that was also wrapped in Velcro, but if you push it close enough, the Velcro would hold it together. And in that analogy, the Velcro is the strong force, and the magnetic field around the magnet is the electrostatic force. Okay, so larger distances, the repulsion is stronger, but at short distances, the strong distance is stronger. Okay, what does that mean? Well, that means that in the sun, for example, in the sun you've got hydrogen, and it is combining to make helium. But you can't just use any old hydrogen, because if you used any old hydrogen, you wouldn't have the right numbers to get up to helium, so you have to use something called an isotope of hydrogen. So you would say that it has got one proton and one neutron, and that way you can see these numbers now add up to 4 and 2. Okay, so that's how it happens in the sun, but we want to do it on Earth. So the next thing that we can do is we need to set up conditions that are similar to being on the sun, but on Earth. So conditions that you need are, you need it to be really hot, and you need it to be even hotter than the sun, because you don't have as many of them, so each one you've got has got to have more chance of hitting. And the way that we do this is something called a plasma. And all that means is that the electrons are now free. Okay, so all you've done is heated it up so much that the electrons are now separated from the atoms. But you've got to keep it that way. You've got to keep it that hot. And the only way you can keep it that hot is if you don't let it touch the sides. And the way that we make sure it doesn't touch the sides is by using magnets. So if you imagine that you've got a plasma, which is really hot, where the electrons are now free to do whatever they want, and you've got a plasma which stops it from touching the sides, and then you can see how this is going to work out really expensive and really difficult to do. So they're your major downsides, okay? Engineering wise, it's really hard to do. and it's going to be very expensive. But the thing that you're going to have, which is the big advantage over fission, is let's go for an example of what's happening inside a fusion reaction. So inside a fusion reaction, if we've got some if we're fusing together these two, for example, the deuterium, then this is our waste product. It's only helium, okay? Nothing wrong with that. So, and we can get these ingredients, the hydrogen, from seawater. So, no radioactive waste. Raw materials plentiful. Okay, and what you'd have then is you'd have a little mini sun on Earth. There'd be no radioactive waste. You can get the raw materials from seawater. Your waste product is only helium, so there's absolutely no reason why we wouldn't do it, except for these two factors. It's very hard to do, and it's going to be very expensive to get started. Once it's up and running, it won't cost very much at all, because your raw ingredients are just seawater, but it is going to be very expensive to get started, just because of how difficult it is to do.